morning, everyone. Welcome to the second day of the Growth Winter School. It's my pleasure to introduce Professor G.C. Anupama from the Indian Institute of Astrophysics. Professor Anupama also did a PhD from IIE a few years ago. And she's currently the director of the Indian Astronomical Observatory at Calibration, which has the Himalayan Chandra telescope, the Growth India telescope, as well as the Gamma Ray telescope. She's also a member of the National Academies and has won many awards, including TFT. She's a co-PI of Growth India, so pay extra attention to her talk. Without further ado.
So last evening you had some sort of an experience with observations, which I hope was interesting enough, although we did have some issues. But anyway, the net result of any observation is that you have a lot of data that you need to analyze and get science out of it, right? So to do that, there are certain steps that you need to do to get some meaningful results out of your data. And today, much of our, today's sessions are all connected with what you do with the data and how you would ultimately get some meaningful results out of your data. Let me start the first steps that we have to do with any data, and I'm going to concentrate on the image data. That is essentially what we do for use for photometry. I'm not going to talk about spectroscopic data right now, but much of what we do for this image data is also something that we do in spectroscopy. Okay, so whatever I'm going to tell you now, a good fraction of it, majority of the steps are what you'd initially do even for the spectroscopic data before you go to actually analyzing the spectrum. Okay. So what is image data? It is essentially the astronomical images. That is a portion of the sky which is recorded on your detector. There is the two-dimensional detectors. And some of the most commonly used detectors are the charge-coupled devices, the CMOS detectors, and the infrared arrays to observe in the infrared region. CCDs are, by far the most largely used detectors in astronomy. And some of the main advantages of using CCDs are that it has a good quantum efficiency, good linearity, and a good dynamic range, all of which we want in any astronomical instrument. Okay. So just a few slides on what charge coupled devices are for people who don't know these. You have the CMOS detectors are what by and large are used in the digital cameras and in your mobile phones to a certain extent. But what we use by and large in astronomy are the charge coupled devices. So these are nothing but silicon based arrays, where you have these pixels, or the pixel that is a light collecting element in the CCD, which acts like small buckets of light collecting buckets basically. Okay. So what happens is that in these pixels there is a potential well which is created where the electrons are stored, and these electrons are generated when a photon strikes on this, okay, with the photoelectric effect which all of you know. So this is how the electrons are generated, and these are stored in the pixel. So having been stored in the pixel, you need to read out these electrons, right? So what is done is that you have a circuit which essentially allows in reading out the electrons. So when you have this potential well created, the region of the pixel which has the most positive voltage, that is where the electrons are stored, then you have to read off. So this is done by a clocking sequence where the adjacent pixel, you make that more positive, so the electrons move from where it is collected to the more positive region. So you keep doing it sequentially. Okay. So the CCD has it's a two-dimensional detector, so you have these rows and columns. Okay. So basically what you do is you have one column here which is the readout column, So you read the rows. So for example, along each row, the charge is transferred here, and the charge gets transferred sequentially this way. Okay. So you keep reading off each pixel, it keeps getting transferred from one pixel to the other. And that is why you're calling it as a charge coupled devices, because it's not read off from each pixel, but it is transferred to another pixel and it is read off. The most used analogy for how to understand how the pixels are read out is what is generally used is what is called as collecting the rainwater in buckets. So you can look at each pixel as a bucket which is collecting water, and then you essentially tip off this bucket first. So this gets emptied. So to initially these buckets are all empty. So what you do is you tip off this into this, it goes like that. Then you tip off this, empty this into this. So you read this. Okay. So you keep shifting. It's like a shift register. You keep shifting the charges and you read them off. So what you're reading of the charges is like you're reading of the voltage, and that you need to convert into a digital form, and that is what we call as the counts. So essentially there are these amplifiers which convert, they read out electronics, converts the voltage into the digital form, and the amplifiers are there which will kind of, there's a gain given so that you have the voltage can be easily read off. And what is of importance here is what we call as the analog to digital unit. So which is nothing but a reflection of the amount of electrons which were collected, which in turn is a reflection of the photons or the flux that has been received from the astronomical source. Okay. To use any detector, there are a lot of things that we need to understand, certain characteristics about the detector, and it's extremely important to know what are the defects that you can expect in such a detector. Okay. So there are various defects that you can expect in a CCD. One is you find there are some bright columns or bright row and bright spots in the CCD, even without it having been exposed to any astronomical source. And some of these, like the bright columns, they are caused due to the electron traps, which is so when there are some electrons trapped in certain columns, when you it can leak out when you're reading the thing, and so it kind of it leaves a trail behind in the column. Okay, so these are called the bright columns. Then you can have hot spots, which is essentially the regions where you have a slightly larger dark current as compared to its adjacent pixels. And when the pixels saturate, that is, it reaches its full well capacity, when you read off, it again leaves a trail behind. So this is called as blooming. And then if you, of course, you have something called the cosmic rays, which Varun talked about yesterday, and this is which happens in all CCDs. This is not a manufacturing or a fabrication defect per se in the CCD chip. It's just that these chips are sensitive to these cosmic rays which are there all over, and you can have a lot of these events which are affecting your images. And then, as is the case in any detector, you have these noises. The read noise is essentially the noise due to the readout electronics, and then you have the thermal noise, which is due to there are these electrons which are generated just because of the temperature, and much of the thermal noise can be reduced to practically negligible limits by cooling the detectors, and typically all the CCDs are cooled to kept in a liquid nitrogen divar, and it is cooled, or you have the Peltier cooling systems. Okay. The growth telescope, the CCD camera which is used there, is Peltier cooled, whereas on the HCT and many of the other telescopes, the CCDs that are used are liquid nitrogen cooled. Okay. And then you can also have you know a slight difference in the sensitivity from one pixel to another pixel. So this also causes some kind of noise level, and you need to have an understanding of what these variations are to be able to obtain the flux that you actually get from the astronomical source. So some of these we need to take care of when we are doing our image data analysis, and I will go through the steps of what we need to do to take care of these defects. Okay, so what is image data reduction? Okay, it's nothing but transformation of the raw images that you get from the telescope, from your detector, into something that is meaningful enough for you to do science out of it. Okay, so what do you need to do? You need to remove the detector and the instrument signature from your images, and then you need to remove all unwanted signals like the cosmic ray events, which has got nothing to do with the object of your interest. And then you do what is called as the astrometric calibration, what we were trying to do yesterday when we had this doubt of did we observe the M77 supernova, right? I mean, we could not really identify the field. So what did Shubham do? Can anyone tell me what was done? If you had paid attention to all the discussion that was happening? Sorry? That the contrast in the brightness was changed so that we could identify the supernova, right? But then there was something else which Shubham did, and based on which we said, yes, this is a region we observed, this is the M77 supernova region, which is what we wanted. How did we come to arrive at that? Yeah, we compared with the bright star, but we were doubtful, right? Because we had a little bit of distortion in the image, so we had doubts. Yes, so what is meant by astrometry? What did we do? How did we confirm? Yes, and? So essentially we try to see what were the coordinates of the field that we observed. Yeah. And what are the coordinates of the supernova? You match it with the supernova is of course not in the center, but nonetheless we knew that it was within the field of view of the detector. Right? So that is what astrometric calibration is all about. And then when you take multiple images of the same field, which we normally do for various reasons, one of the main reasons is to improve the signal to noise, that is you want to enhance the signal in your data. So when you do that, you stack these individual images or you combine them together. Okay. So when you combine them together, you have to ensure that all of them are perfectly aligned so that they don't introduce further distortion. So that you do astrometric calibration and then you can stack them, or you can stack them even without doing an astrometric calibration by matching the pixels very well, and then you can do the astrometric calibration. Okay. So you can do it either way, or you can do calibration and stacking together. Packages are available to do that. So let's go on with each of these individual steps now. So as I've been saying, the data itself, contains your astronomical observations. What these are, I don't need to go into that. But what is important is that you need to take certain calibration images. Okay, so these are the non-science images that you need to take. Okay, to help you in removing the detector and the instrumental characteristics from your data. So what are these detector calibration frames? These are what we call as the bias and the dark frames, and then the flat field frames. And for the science calibration itself, in certain cases you might need to take images which are slightly off the actual source area, where you have a slightly blanker fields. If this is in case your objects are extended objects and they more or less fill up the whole detector. So you do that because you also need to subtract the photons which are coming from the night sky. Okay. So for that, for the what we call as a sky subtraction, you might want to take another image which is offset from the object of interest. And then of course you have to have observed standard stars for photometric calibration. What are these standard stars? Yes? I'll come to that. So what are these photometric standard stars? These are regions of the sky where the stars have been very well studied and they're found to be non-variable. Their fluxes are well understood, and so these can be treated as standards. The magnitudes are treated as standards. So essentially, you will hear more about it in the next talk on how to do this photometric calibration. So you need to have observed these objects also. Okay. So in the case you have CCD images with multiple CCDs, these appear like a mosaic, and what I have shown here is just an example of how such a mosaic CCD data would look. What you see here in between, these are the gaps between the CCDs which have been mosaiced together. Okay, what is bias? There is always a base voltage level that is applied to the CCD. One of the reasons for doing this is you try to keep the potential well to a certain level so that even a faint photon which is striking onto the detector can generate sufficient number of electrons for us to be able to read out. Okay. But one needs to be very careful, and actually this is what the bias level is determined by the gain. Okay. So you need to be very careful also that you do not have an extremely high gain. If you do that, you will be reducing the dynamic range of the detector. What is meant by dynamic range? Anyone make a guess? Not you, I think you have experience. I want somebody else to tell me. What does the term itself, what does it indicate to you? Yes, in a certain sense. Yeah. So what is important here is that we need a detector which can not only detect the fainter photons but also the brighter ones, right? It does not always happen that, but we need to have a good range of fluxes that can be detected. Okay, we don't want to have a detector which is tuned only to the faint objects, as a result of which you're going to saturate all the bright sources in the field. Okay, so you're not going to be able to get any information about the bright sources in the field. We don't want to have such a situation. We don't want to have a detector which cannot observe bright sources, nor do we want to have a detector which cannot observe faint. So you have to have some optimal range. Okay, so this is the dynamic range that we taught. The CCDs have a fairly good dynamic range, and we keep the bias level at such a at a level where we have a good enough dynamic range. Okay, so it is determined based on what you want to do with your detector. So sometimes the instruments also have the option of changing the gain. So if you're observing a faint source, you can, and you're not interested in the bright objects, you can have a slightly higher gain so that you can detect your source with a shorter exposure time. Okay. So what are these bias frames? These are nothing but 0-second exposures. So what is happening is you're just reading out. Okay. So when you do this, the base voltage that is existing all the time in the potential well, which is giving rise to certain electrons, that is read out. Okay. So this is giving you the this level which is of voltages which is there in every pixel, which you have to subtract out from the image. Okay, so you need to ensure that these electrons are not treated as the electrons arising from the photons of the astronomical object. Okay, so they need to be subtracted out. So what you do is you obtain multiple images, either in the beginning of the night and the end of the night, or you obtain throughout the night. The advantage of obtaining bias frames throughout the night is that if there is some problem in your electronics which is causing some kind of a drift in your gain, which can happen, then you find that your bias level is not the same throughout the night. Okay, so you might want to keep doing this. This is also giving you a health check on your system, and it also depends upon how accurately you want to get your photometry done, in which case it is always better to use the bias values obtained as close as possible to your astronomical observations. Okay, you just read it off. Dark, I'll come to that, how it is different from dark. It means that you're not really giving any exposure time. Okay, you're not integrating for a period of time. Your detector is on. Yes, it's powered on. So you take these multiple bias images and then you combine them, you do a median or an average combining. So why do you do this? To reduce the noise, which is essentially the read noise that you have. Okay, you do that, and then if there are some spurious events which are struck, and some, like for example there could be some cosmic ray hits, so when you do this median combining, they're not going to be in the same position in all your frames, so they get removed out from the final combined frame. Okay, you create what is called as a master bias, which is median combined bias frame, and then you subtract this bias frame from all the images. Okay, so this way you have taken care of this the zero level voltage which is applied, the base level voltage that is applied. Sometimes CCDs can, yes, in principle it should not. If your system is stable, it should not. Okay, sometimes you can suddenly find that the CCD is showing some sort of a horizontal pattern, like for example, which happens quite often in India, for instance, if you have some issues with your earthing, okay, there can be some pickup, so you'll find a pattern, and it can so happen this pattern doesn't even remain stable. Okay, so what do you do under such circumstances? What I told you in this part, when you're doing the subtraction, you're doing a two-dimensional subtraction, that is pixel to pixel, you're matching and you're doing a two-dimensional subtraction. Okay, so what do you do when you have something like this? You can just take a median, you can take a constant value and subtract out. Okay, so this is what you do in bias subtraction. There are various other things. You can have what is called an overscan region, where you have some extra pixels which are just read out. That will again give you this bias value. You can use that to subtract, and some of these things will be shown in the module. Dark is you do not expose the CCD to any light, and then you obtain several images. And this is what by and large, in very well cooled systems, you don't have much thermal noise, but otherwise you have this thermal noise which is a function of the exposure time. Okay, so you need to, if your detector has thermal noise, detectable thermal noise, then you need to take dark frames which are the same exposure time as your object frames, and that you have to subtract out. Now when you're subtracting the dark, it has bias, so you don't need to do an independent bias subtraction. Okay. The next thing is flat field correction. Why is this done? This is done to take care of the pixel to pixel sensitivity variations. Now how do you do this? To do this, what you need to do is, you need to expose the CCD to a uniform source of light. So your source is uniform, like a continuum source for example. You need to expose the CCD so that every pixel in principle is getting the same amount of flux. Okay. So when you have such a source and your CCD is illuminated by such a source, in principle in your output every pixel should have the same counts, but you don't have that, right? So this is a pixel to pixel variation. So how do you take care of this? You expose the CCD to a uniform source of light which can be within the dome, or you expose it to the twilight sky, okay, when the sky is bright enough that there are no objects seen. And the third is that you can actually use the night sky itself as a flat field source. But for this, what you need to do is you need to observe blank regions of the sky, and then you will have to combine them. This does take up a lot of your observing time. So by and large, people would prefer to use, a twilight sky. Now, what is shown here is the flat field image from 3 different sources. The first one is the HCT image. The other 2 I just took it from the web. And the flat field image shows a lot of not only the defects in the CCD, also if there is some dust in the optics, that also shows up. Like you can see some of these circular patches out of focus. These are all what are called as the dust rings. All this can be removed from, all these effects can be taken care of when you do the flat fielding. And then you also have this fringing which we saw in yesterday's images, that can also be taken care of when we do the during the data reductions. Okay. So once again, you another thing to remember is that you need to obtain flats in each filter that you're observing your science object. Okay. So once again, you take the flat fields, you subtract out the bias from the flat fields, and then you do a median combining of the flats in each filter individually. Okay. You can use the median or the mean, but the median is always better, because you tell me why. Yeah, it can kind of add to the average. Yeah, that's right. Okay. So having obtained these master flats, okay, what you do is you need to normalize them. Okay. Now, what do you mean by normalizing? And why do you need to normalize? What is important in our data? Signal coming from the source, right? So what will happen if you don't normalize? First of all, what is meant by normalizing? Yeah, right. So why do we need to do this? Yeah, so that the flux that you're getting from the source is not, or the counts that you're getting from the source is not altered by the flat field counts, right? Flat fielding? No, you normalize the flats and then you do the flat field correction. So what do you do in the flat field correction is that you make the master flat, okay? You can either normalize the individual flats and then median combine them and make the master flat, or you can make a master flat and then normalize that, okay? And then how do you do the flat fielding is you divide your science data, which is bias subtracted, by the flat field frames, okay? So this will take care of the pixel to pixel variation. How does this take care of the pixel to pixel variation? Good. So let me just show you, for instance, let me go back to this here, okay? So there I have pointed out a bad pixel. Suppose I take a row cut in a normalized flat. What will happen? I plot it. In principle, I should, if I take this as the counts, pixel number, it will go like this. But where the bad pixel is, you can see it as a dark spot there. You will have a dip in the sensitivity and then it goes like that, right? So if this level is 1, when I divide by this along this row, this will get corrected for, okay? So that is what the flat fielding does. This is how it corrects for the pixel to pixel sensitivity variations. The next thing is the fringing, right? How do you, why is this fringing happening? This is basically happening in what are called as the thin CCDs. You have multiple reflections in the, especially in the red region, and this can give rise to interference, which causes these fringes. Okay. So how do you take care of the fringing? Fringing is again additive. So what you do is you take the flat fielded images, and then you can actually take the data itself. Okay. Since this pattern is there in every single frame, you can use all the data for the night, and then as long as you don't have too many bright sources in your images, this works out well. Then when you median combine them, you will be left with and then you median combine all your images, smooth it out. Okay. So when you smooth it out, you're kind of left with all the astronomical sources more or less smoothened out. Okay. You have a sort of an image cleaned out of the astronomical sources. So this you can treat it as the night sky flat, for instance, and then the heavily smoothened night sky flat will give you this uniform background source. So which when you subtract it from this night sky flat, you're left with only the fringe pattern. Okay. So this you can subtract out from the images which have the fringing defect. The last thing that we need to do is removing the cosmic ray events, because these are not really associated with our source. Now here are examples. The first one is the HCT data, where fortunately in this particular image we didn't have too many cosmic ray events affecting us, whereas the next set of images that I'm showing are some HST images which I kind of picked up from the net. And there you can see, you see a lot of small white spots all over, right? Those are the cosmic ray events. And that, when you remove that, you see it's a much cleaner image. You will understand more of the cosmic ray removal in the module. The basic thing is to identify how do you, I think yesterday Varun mentioned that how you would identify, because you have these profiles which are very different from the object profile. So that is one way of identifying these sources and removing them. Okay. So then astrometry, as we discussed in the beginning itself, this is nothing but matching your pixel to the position on the sky. Okay. So this you do by comparing with standard catalogs where the coordinates of the objects are known. So you identify your field with that, and then you get these, then you are able to match your pixel to the sky coordinates. Okay. So this again will be there as a part of the module, and then you have the stacking. So finally this is the summary of the various steps that we need to do in image data reduction, and which you can actually do now with the module. Thank you. No, it's closed. Yes. Every night flats are obtained, biases are obtained. Okay. I mean, you can, if for example you are observing a transient source, and then there's no flat obtained for that night, you can probably use the nearest night. But in principle, the best way of doing it is that it is done that way. For instance, what we do with the 2-meter HCT is that every night and every morning during the evening twilight and the morning twilight, flats are obtained in all filters, irrespective of what the observational program is for that night. Whether it is spectroscopy or photometry, whatever is the proposal, we don't care. But flats are obtained every night. Okay. So this can be used by anybody else also. Whatever data is obtained in that night, you can do that. In what? Space telescope, yeah, the calibration frames are obtained, but there you can use the night sky to get the flats. Why the sky flats are more preferred than dome flats? Dome flats can give rise to certain other kinds of problems. One is like if it is not properly designed, then it can have issues of not being able to illuminate the full mirror, for instance. Then you don't really have a uniform source of light. And the other thing is, it is always good to have more or less the same, the light goes through more or less the same path as your object, okay, in which case you need to have a lot of optics which will give a similar F ratio when you're observing the dome flats. And the other thing is that you're using an artificial source here which may not really be uniform and across the wavelengths, okay, so you might have issues with that. Can discuss later.
Okay, right. So first question: did everyone get a chance to download the updated version of the module that was sent out last night? No problems with that. There was another email sent out this morning about installing. Yes, right. Yes. So, so for today's module, based on what happened yesterday, I think there was some confusion about the paths and everything. So I've decided to run everything on my laptop from the Docker that you all should be running. So please try to use the Docker that was supplied to you, because it has all the necessary software that we'll be using in this module. And I will be running on the same Docker, so in principle we should all have the same paths. So whatever path I said, you can set the same path and we should get the same results, everyone. So I sent out an email earlier today about installing these 2 additional modules. So in case you haven't had a chance to do that, just in the terminal that is running the Docker, just type pip install. So these are just 2 modules that we'll be using in this session. So you can just run it from the terminal and it should work. Okay, right. So when you get a chance, please open up the unsolved version of the notebook. The solved version is only for me to cheat from. You should use the unsolved version to start off with the process of image reduction. So these images, the ones that we'll be working on today, these were actually taken with the Growth India telescope. Except these are not images from the last night. These were taken about a couple of weeks ago, but they will demonstrate the general process of image reduction. And in this case, we are actually looking at a field that contains an interesting variable star. So, and you'll be working with the light curve of this variable star in the future light curve analysis module. So, just so you know where all that photometry comes from, we'll actually be reducing this data to show you how you get from a raw image that comes from the telescope to a reduced image where you can extract photometry from, which is the subject of the next module. So I'll just wait a couple of minutes in case you haven't had a chance to download the notebook or run this command. So just run this command and you should be able to install the modules that we'll be needing. So I'll just wait there. Perfect. So the first thing that we'll do is, as Anupama already mentioned, is to create what is known as a master bias frame. So the idea is you take exposures with a telescope with 0 exposure time to subtract off the offsets that are introduced by the detector, which does not reflect the true brightness distribution on the sky. So we'll start with just importing a few modules. So this should just work smoothly. We're just importing some modules for plotting and for doing some statistics on the images. So if you move on to the next cell, so just make sure your path is set to this. This is exactly the path that should be there in the Docker. So if you set this path, it should work. Right, so once you've done that, what I'm doing here is just, I've sorted all the calibration files into folders. So I'm just reading the files that are there inside that folder and then loading them up into this NumPy array. So this is a 3-dimensional NumPy array with the images stored in, the multiple bias images stored in as different elements in the array. So so if you run this, it should say there should be 3 bias files that are there in the folder, and then it will, once these files are loaded, I'm also plotting up one image, one bias image that was there in that folder, just to show you what a typical bias frame from Growth India looks like. This can take a bit, but should come up. Yes. Yes. Okay. The path. Okay. So does everyone have this single bias frame plotted up? Does it look okay? Okay. Right, so I just wanted to notice the general pattern on this bias frame. So as you can see, the offsets, they vary with the position in the detector. So the left hand side of the detector has a larger offset, so the bias values are larger over there, whereas the right hand side has lower bias values. So we have to subtract this offset off from the real images. So just keep this pattern in mind. We'll see it later in the actual images. Right, so the next one is just an exercise for you. We did create a master bias frame. So if you see this array called master bias right here, can you try to just plot this master bias using, well, basically the same, pretty much the same commands that we used to plot a single bias frame. I'll keep this up here. So in the next cell, just try to plot this master bias. Also, just so you know, this, what this command here is doing is that, so we have all the bias images in one array, which is a 3-dimensional array, and what we're doing is we're asking NumPy to stack along the images, along the different images, so that what you get effectively at the end of it is an image which is median combined from all of the individual bias images, which is why this parameter axis equals to it stacks along this specific axis that we asked for. Okay, so how many of you were able to plot the master bias? Okay, perfect. Okay, how many of you are having trouble plotting the single bias? Any major issues yet with plotting the single bias? Okay, I think I'm going to move on. So let me just show you what the master bias looks like. Oops, I'll just, yeah, I already made the master bias, yes. So if you look at this command, this is what this is doing. I did a median combination over all the bias images. So you just have to plot this, yes. Yeah, okay. So this is what the master bias looks like. As you see, it's pretty much has the same structure as we saw in the single file. Right. The next part that comes is the flat fielding. So as you already heard, flat fielding is about removing the pixel to pixel sensitivity variations to make sure that the image of the sky that you're getting does not reflect the sensitivity of the telescope and the detector combined in the image. So as before, I will change this path. The path in this case should be, so just copy over this path. Okay, so as before, it's exactly the same path, except it's a different folder. It's, instead of bias, it's in flats now. So if I run this, it should show up what a single flat frame looks like. So just to walk you through what's going on here, I'm again loading up all the flats that were there in this folder, and then I am subtracting off first the master bias. So the flat itself also has the master bias offset inside it, and we want to remove that before we do the flat combination. So I'm taking one image, which is the flat field, subtracting the master bias, and then normalizing it. So, okay, so again, I'm taking each flat field image, which is in this, subtracting off the master bias, and then normalizing the flat by its own median, so that irrespective of what the actual counts in the image were, everything is now normalized to the median counts in the image. Any questions about that? Why this is doing that normalization? I'm just dividing the entire image by its own median. And then I just plotted up, I basically use the same command as I did for the master bias. In this case, I'm just plotting the flat frame. So this is what a single flat frame looks like. How many of you got to this step? Okay, perfect. Okay, so just take a note of the count. So you see, all of the counts in the image, the color bar, they are normalized to 1. So everything is normalized with respect to some 1 value. Okay, any major issues in running this yet? Okay, so It's again because the median is always more robust to outliers. So imagine if you have a cosmic ray somewhere in the image, then a mean will always be affected by that cosmic ray. It might just produce a weird value for the mean, whereas the median is much more robust to outliers. Sorry, what? Okay, okay. Right. So the next exercise is to just do exactly the same what we did in the master bias frame, plot the master flat frame. So in this case, I've left it as an exercise to actually produce the master flat frame. So what you want to do here is you want to go back to this command here, which does this master bias equals to this median over this set of images, and you want to repeat that to create a master flat frame. Yes, so just note that all the flat images are stored in this array. So just make sure that you're running a median combination over these images for the flat frames. Yes, that is a bad column. That's the one that Anupama mentioned about where you can have electrons accumulating for no reason. It's just a defect in the detector. Yes. So all detectors have some level of defects. You're just seeing that. Yes. Yes. So okay. So let me. So some people are worried because they are seeing a single line in the image somewhere. That's a bad column. That's a known. At least I think it's a known defect in the detector. So it's one of the defects that Anupama mentioned, which can happen because of electrons accumulating at some specific location. So those are bad columns, and in a real image reduction, you would actually account for them. You would typically previously know where the bad columns are, so you can not observe your sources on top of that bad column. You don't want to do that. Not always. Sometimes those bad columns are just too bad. You can't remove them. You just want to keep your sources of interest away from that bad column. Yes. Okay, so I'm going to go ahead and produce this thing. So let's. Whatever, it should be median. Okay, there's a median. 3. Yeah, it's the Docker. I don't know why it is. Yes. So this is so if you run this command, which what I'm doing here is again taking the flat images and median combining it along one axis and plotting it up. So you should see something that looks like a flat field that looks like this. It's because of it says matplotlib. It shows up at some scales, shows up at some not. Yes. Okay, how many people got to this step? How many people are having major issues getting to this step? Oh yes, so what I'm doing here in the plot command is that I'm setting the minimum and maximum scale of the image. So the idea is that I'm computing what is the median and standard deviation of the image using this function here. It's called sigma Clipstat. It's a astropy function, and then I'm scaling the image so that so that all of the counts displayed in this image are between the about 5 standard deviations below and 5 standard deviations above the median of the image, just so you see what the structure is like. Otherwise, typically what matplotlib will do is that it will scale the image according to the minimum and maximum of the image, and just in case there is a cosmic ray in the image, you won't see anything in the plot at all. So just scaling it so that you actually see the structure that is there in the image. I mean, as long as it's some standard deviation, yeah, it should be fine. Yes, just to get rid of the very bad outliers. Yes, yeah. So this is only for visualization purposes. It does not affect the image reduction at all. No, it is there. It's just not showing up. Yeah, it is there. Yes, yes. Okay, so if there are no major issues, I'm going to move on to the next step, which is, so effectively what image reduction is to get the true distribution, brightness distribution of the sky from these raw images. And the general thing you should have in mind is that the image that you record is a multiplication of the So the flat field multiplies on the true brightness distribution, and the bias is an offset that adds on to it. So image reduction is all about just solving this equation. So if this is your image, you subtract the bias and divide it by the flat, you will get what is the true brightness distribution on the sky. And this is exactly it's a pretty straightforward arithmetic operation once you just keep this equation in mind. Okay, so now, now I'll move on to actually using these master bias and master flat frames to reduce real science data. And in this case, you again need to change the path. The path in again should be .. Yes. So right. So okay. Anybody having major issues getting to this step so far? Everybody has a master flat and a master bias ready? Okay, good. So what I'm doing here again is, so this folder now has all the science images that we want to process, and what I'm doing here is just plotting one of the science images to show you what it looks like. This is a raw science frame. It has all the bad effects that were introduced by the telescope and the detector, but you should just have a look at it just to see what a raw image looks like. Okay. It's just one image, yes. So this is one raw image from the Growth India telescope, and as you can see, the pattern that you should be looking for is this. You see this trend of increasing counts on this side? This is the bias that is introduced on top of the science frame. And you want to subtract this bias and divide it by the flat field to get what the true brightness distribution on the sky is like. Yes, yes, it should be approximately the same for the same detector, at least over some period of time, yes. It's a detector property, yes. Different detectors have different patterns, really. Possibly, yes, yes. Okay, everybody able to plot this science frame, the raw science frame? Raise your hand if you are able to plot the science frame. Anybody having major issues? So by the way, I will pull up this path just so that in case you want to look at the path, this is, if you are using the Docker, this should be the path that you will find the science frames in. Okay, questions, issues, problems? Okay, so if there are no major problems, I will go on to the next step, which is actually applying the calibrations that we have to these science images. So, okay, so what I'm doing here is I'm looping over all of the science frames that we just listed from the previous cell, and so this is the raw frame. I'm reading the raw frame. This is the data. This is the header. This is the data, this is the header, and then I am producing a new array, which is the processed data, where what I'm doing is I'm subtracting the master bias, raw data minus master bias, and dividing it by the master flat. This is exactly solving the arithmetic equation that we saw a few minutes ago. I'm subtracting the master bias, dividing it by the master flat, and then I'm writing it to a file, which is called basically the same name as the science file with a proc.fits, which just means it's a processed file. So let me run this cell. Yes. So it's probably running. Okay. So everybody able to run this cell? Raise your hand if you are able to run this cell. Okay, how many were able to run this cell so far? Okay. Oh yes. It should just be it's not really plotting anything yet, so it's just writing the files to the disk. Is it? Just a moment. It means you have there's a 0. Sorry, what? Oh, it should just be .proc.fits. It's just saving the file as with the same name with a suffix to it which says .proc.fits, means it's processed. It's exactly this name, so it's the folder plus the name of the file plus proc.fits. axis. So what we've done is we've loaded all of the flat frames into a 3-dimensional NumPy array. So imagine it's like a stack of, so there's one image, another image, another image. What we want to, so if you want to median, there's so many axes you can median against. You can median along this axis, you can median along this axis, you can median along this axis. What we want is a median along the image dimensions. So axis equals to 2 says median along the image directions, so that what you get effectively is a, that's because of the way I loaded the frame. So if you see this, so this says that for each layer in the array, you're loading in the data into that specific layer, and I want to median along that layer, so that what you get is a median combination along that axis. That's what axis equals to doing, because I think by default NumPy will not median along the correct direction. You have to specify that you want to access along this. Okay, so what I'm doing here is I filled in the next cell after that one, and I'm just plotting two of the reduced science files. So it should look something like this. You should first open the data, load it with AstroPy in an array, and then plot it. Yes. Yes, it's an electronic offset in the detector. That's always there. Yes. No, flat is the variation in the sensitivity of the pixels. So each pixel may not be have the same sensitivity to incoming light, and that's why it multiplies onto the science image. Whereas the bias is an offset that you want to remove. Usually the natural background light is not as much of a problem in the optical. In the near infrared, things are different, but in the optical, it's not really something you should be worried about. Yes. All right. So this is what the reduced image should look like. How many of you were able to run some version of this to get an image that looks like this? Okay, I see one hand. Okay. So the thing that you should notice is that the offset variation across the image is now not there. It's more or less plain. The edges of the image are still dark, and that's because of vignetting, where it's just that the telescope optics does not allow light to get into this part of the image because it's such a wide field. Okay, so just so you know, this is pretty much all there is to image reduction. This is what a true image of the sky actually looks like. The subsequent steps, depending on how much time we have, the subsequent steps are just refining on this image to remove more and more artifacts from the image. But in principle, this is all you need to get science data out of. This is a reduced image, a true image of the sky that does not have any of the artifacts that were introduced either by the detector or the telescope. I have not stacked anything yet. These are individual science images. Oh, so there are two. I just plotted two of these images. Oh yes. So this is where I'm just reading the file that was written to disk, and then I'm plotting it. Okay, so far we actually have reduced images, but the next thing that I had in my module, which is probably going to be the last thing that we do, is let's see. So the next part of the module is to remove cosmic rays from the image, where the idea is that in the duration of the exposure that you had, there were probably some cosmic rays that hit the image, and the way to identify them is to look for very sudden variations in intensity in the image. So imagine you have so a normal star, if you look at a normal star, then a star always has a shape which reflects the PSF, the point spread function of the image. So you would get a smooth variation that looks like this if you take a cut across the star. A cosmic ray looks very different. A cosmic ray would typically look something like this. It's a sudden delta function that just hit the detector, and it's this change, it's this difference in the shape that allows you to identify what are cosmics and what are real stars. And out there are actually quite a few implementations of these algorithms that deal with cosmic ray rejection, and I wanted to use one of these, which is called, so this is a fairly popular cosmic ray removal algorithm. It's based on LA Cosmic, which is a routine to detect cosmic rays, and this is a this module that we just installed before the start of the session, this is a Python implementation of this same module, which is LA Cosmic. So let's see. So if I run this cell, okay, so I just wanted to show what a typical cosmic ray mask looks like. So even if you haven't been able to run it yet, but I think you should just take a look at what a typical cosmic ray mask looks like. So what you have here is basically the same image, but what this algorithm did is to detect things that look like this, and it created a dot wherever it found those things. So yes. Okay, how many people got to this step? Okay, there were, okay. So I think I'll end with astrometry. I think if you're 5 more minutes, yes. So okay, so so we can talk offline if you are not able to get to this step, but I just wanted to show what astrometry is about, because that's another important part of reducing an image. So as Anupama said, astrometry is all about figuring out where the image is on the sky, and effectively what it turns out being is matching patterns of stars. So imagine you have, the idea is that suppose you have stars in your image that are randomly positioned like this, and you ask the question, what if I join these lines along stars? And then you want to match these pairs of stars to a catalog of known positions. So imagine you have a separate known catalog of known positions. This could be, so we live in the era of big surveys, so it's very likely that the position that you're observing has already been observed by some other survey. So you take that catalog. So this other catalog will also have the same stars, because it's the same part of the sky. So the idea is that this other catalog also has the same pattern on the sky, and you ask the question, does this pattern that I see in the catalog match this pattern that I see in the image? And if it does, you actually know what is the position of the image, what is the orientation of the image, and what is the scale of the image in terms of how many pixels corresponds to how many arc seconds on the sky. And that's all that there is to astrometry, and basically all astrometry software solves this problem. Yes, I mean they use more complicated, I mean this is just lines, but it can be quadrilaterals, triangles, really anything. Let me show you. So what I'm doing in this module is actually just using a code that was written by Dan Purley at Liverpool, which is a fairly simple to understand code, which is effectively solves this problem, which is to match stars in the image to stars in the sky. And let me just try showing what this looks like. Okay, so if you keep an eye on your terminal while you're running this, you will see that it detected few objects in the image, and it's matching it to a catalog of known images. In this case, we are actually matching it to the 2-mass catalog, which is whole sky, near infrared. And what it did was it found so many matches between the stars in the image and stars in the catalog to figure out what is the position and orientation of the image with respect to the catalog. And just to show you what matches it found, this is the, just give me a moment. So what this code also produces is a list of matches, which is list of shapes that it found while trying to solve this problem right here. And once it loads up, okay. So these are the matches that it found in the image. So what it did was that it asked 2mass, give me the positions of the stars that you know about, and these are the positions of the stars in my image. Can you match any shapes? Could be triangles, straight lines, quadrilaterals, really anything. And does this look like any of the matches that you see in the catalog? And these are the good matches that it found. So you see, there are this. So this pattern is called an asterism. It's just a name. It's asterism, where you effectively match patterns in the image to a pattern in the catalog. And these are the good matches that it found. So once you have this kind of an identified pattern on the sky, you immediately know what is the position of the image, because you know the position of these stars. You know how big is the image, because you know the positions of these stars. And that gives you very accurate information about where this images on the sky. And you want to use this if you want to say, measure the photometry for any star in this field, because you want the positions of the stars with respect to some absolute coordinate system. So I just had one more part in this, but I don't think we have time, which is to stack images. But I think if you work through this module, it should be straightforward. The solved versions of the module will be available online, so you can try to run them. But really, after this step, it's really all about, because you know the position and orientation of the image now, you can stack those images very accurately to get a deeper image than what you would get from a single science exposure. So, Mansi, I think, yes.
So the module, next module is actually built on the results of this module. So you've now reduced the data, then you're doing photometry and subtraction. So if you haven't reached this step, then take some time to try to debug it. But for now, let's go have some tea and come back in a minute. Okay, and let's thank Ishari.